Hello everyone, my name is Chen Liang. Today our group will introduce talk about a better continual relation instruction, a rethinking enhanced example or Ansible framework. Relation instruction is a fundamental and critical subtask in natural language processing. Its primary objective is to identify semantic relationships between entities mentioned in unstructured text and classify them into predefined categories. Here are the related work. Here are the challenges. In previous work, continual relation instruction has typically been decomposed into two key challenges within the task: how to enable the model to more accurately identify relationship between entities, as a task-analytic class incremental continuous learning problem; how to effectively allow the models to distinguish the type of task from the input, thereby avoid task identification confusion. And here's our contribution. We invoked a noise-driven knowledge transfer mechanism, a rethinking cascaded voting mechanism, and a EOE framework. Here's the end of the introduction.
Hello everyone, I'm Wang Ziyi. Today I will present our novel approach for continuous relation extraction. Let me begin with our noisy-driven knowledge transfer mechanism. Traditional continuous learning methods typically employ three distillation strategies: using new task data directly, utilizing old task data, or relying on generated old task data. Our key innovation lies in using purely noisy data for knowledge distillation. This approach offers significant advantages. No need to access old task data. Random noise is simpler to generate, and we also avoid task confusion between old and new tasks. Given new task data, generated noise distributions, and teacher-student models, we compute the loss function using cosine similarity to align model outputs. Our algorithm first generates noisy data from multiple distributions and mixes it with new task data. This enables the model learning new tasks to simultaneously acquire knowledge about previous tasks through exposure to noise, effectively achieving continual learning objectives. Building upon NKT, where each expert gains comprehensive historic knowledge, we propose a rethinking cascaded voting mechanism. When input data can't be easily classified, this allows every expert to participate in task identification. This process unfolds in two stages. First stage, if the bot model and the primary expert reach consensus, we directly determine the task type. If they disagree, we proceed to a second stage where all experts participate in global voting, yielding a more robust collective decision. Integrating both NKT and RCV mechanisms, we establish the array EOE framework. During both training and inference phases, we keep the feature extractor for reason. In training, we train one expert per task, while using NKT to ensure each expert inherits knowledge from previous tasks. During inference, we employ RCV for accurate task identification. Our framework effectively eliminates the knowledge isolation among experts, enhances task identification accuracy, and consequently improves the model's overall performance and robustness in continual relation extraction.
The final part is about experiment. We choose traced and fieldwork dataset. We use two key metrics for continuous relation extraction evolution. The average accuracy measures mean task accuracy after full training. The task discrimination accuracy evaluates task identification capability. This is some specific citing and detail. This is experiment result. It is observed on whether a fieldwork dataset or traced dataset REEOE achieved best performance on most tasks. And this is elevation study. It is shown that when used NKT alone, it minimal improvement, RCV alone performance degradation, but when combined them together, achieved best result. So in this work, we proposed REEOE, a concise and effective framework for continuous relation extraction, and it has two key components, NKT and RCV.